everyone, I am Dr. Feride Kulalı and we are here today for the Physics 2 class for the Department of Industrial Engineering, and the topic is RC circuits. It's not so easy, but there's nothing to afraid of if you follow me really carefully. Okay, let's start. And previously we talked about the direct current circuits. In the last lecture we talked about direct current circuits, but they contain only resistors and the batteries. In direct current circuits containing capacitors, the current may vary with the time. If you remember, if we have only resistors and the batteries in the circuit, the current in steady state. What was the steady state? The steady state means the magnitude of the current equal for each segment of the circuit. But for the RC circuits, the current still in the same direction, because as you remember, direct currents means the direction of the current is constant. There is no change in direction. The direction still same, constant, but the magnitude of the current will change. Remember how we describe the current? It was I. The amount of charge which passing through from a cross-sectional area per unit of time, and we describe it as delta Q over delta T. But now it's variable vary in time, so we can write it as instantaneous current as dq over dt. So the quantity is time varying. We will use instantaneous version of the current as dq over dt. What about the EMF, electromotive force? It was the ideal potential difference between the terminals of the battery if there is no internal resistance. So the potential difference of the battery, V, can be epsilon EMF, the electromotive force, remember from the previous class, is equal to EMF, the electromotive force, if we have an ideal power supply in the circuit. We talk a lot about the resistor, so I'm passing it. What was the capacitor? If you remember, the capacitor was the member of the circuit which store energy. So when we connect a power supply to the capacitor, we will charge the place of the capacitor positively and negatively. So the positive side connected with the positive side of the power supply will be positive, and the other side will be negative. And the capacitor has a capacitance, which means the capacity of the capacitor, like a capacity of the bucket. So the amount of the charge which accumulate on the place is limited with the capacity of the capacitor. We call as capacitance. But if we don't change the shape of the capacitance is constant. So we choose a capacitor and put in the circuit. Now, what about the charge which accumulates on the place? If we think about the charge Q on the each plate, it will be directly proportional with the EMF source which we connect with the capacitor. So it's directly proportional with the epsilon, or previously we said that I'm changing it because you remember maybe this version. The charge on the each plate directly proportional with the potential difference which we connect with the capacitor. But there is a constant of this proportionality, and we call this as capacitance of the capacitor, which is constant if we don't change the shape of capacitor. Okay, remember this formula, And here the potential difference between the place of the capacitor, so we will call it as Vc. Okay, and by using this formula also we can write the capacitance equals Q over V, or if you want to write V capacitance, it can be Q over C. Okay, so we will use different version of this formula. So I write each version of this, and you remember the potential difference between the place of the capacitor is Q over C. Okay, we talk about each member, so let's start to charge the capacitor. And here you can see there's a switch, open switch. If we connect this switch to the point A, when the switch is thrown to position A, the capacitor begins to charge up until the charge in the capacitor becomes C times epsilon, C times EMF. The maximum charge of the capacitor should be equal Q equals C times epsilon. Okay, and remember the Kirchhoff rule, and we will apply the Kirchhoff rule to obtain an equation for this circuit. Due to Kirchhoff rule, we can choose a direction. Let's choose a direction consistent with the EMF source. So the current should be on that direction, from higher potential to lower potential. You can choose the direction of current on this direction first of all, then we will choose the other way. And if you choose this direction, the EMF source, the potential difference on the EMF source will be positive epsilon. And think about the potential difference between the legs of resistance. It will be minus, because on the opposite direction, minus IR. And if you think about the potential difference between the place of the capacitor, it will be minus Q over C. So Kirchhoff rule says that the total potential difference in a loop should be zero. So all of these totally should be zero. We obtain the equation due to Kirchhoff rule for the RC circuit. Okay, but let's think about initial time. Initially, the time is zero when we just close this circuit, close this switch. T equals 0. The current starts to flow, but the charge has not accumulated yet. So the charge in the capacitor is 0. So we can say for initial time t equals 0, there is no charge on the capacitor, so we can simplify this part. And if you see this, epsilon equals IR, you can write epsilon equals IR, which is basically Ohm's law. So how you can calculate I here? If you take R the other side, I naught at the time 0, I naught will be epsilon over R. And the time 0, if you think about the potential difference between the place of capacitor, also will be 0. So for initial time 0, we have maximum current, which is E over epsilon over R, and the potential difference between the place is 0. It is the minimum potential for the capacitor. Okay, while we are charging capacitor, as the plates are being charged, the potential difference across the capacitor increases. Once the capacitor is fully charged, the current in the circuit will be 0. Or in other words, when the maximum charge is reached, the current in the circuit will be stopped. the potential difference across the capacitor mesh that supplies the battery, so the maximum potential difference on the capacitance will be equal the potential difference between the potential difference of the EMF source. So we can write the maximum potential becomes EMF source, equal to EMF source. And here we can use the previous equation again to obtain what is going on between these two time intervals. If we wait enough while the time approach the infinite, as you can see here, the potential difference between the capacitor will be equal the EMF source. And what about the current? The current will stop. So we can say if we wait enough, the current will stop, so it will be 0. Now we will write again before the previous formula which we obtained here. Epsilon minus Q over C minus IR equals 0. Okay, can we use this formula to obtain a formula for the current to understand what's happening between these two time intervals? If you want to write a formula for the current here, we can take IR to the other side. So you can write IR equals epsilon minus Q over C, and take the R to the other side, and you can write I equals epsilon over R minus Q over C, RC. We take R here. And finally, as mentioned before, now the current is not constant, changing by time, so we can write it as dq over dt. dq over dt will be equal epsilon over r minus Q over RC. Okay, we obtain this differential equation and we will use it to calculate the charge any time of this event, of this process. We have the formula dq over dt epsilon over r minus q over rc. How we can solve this problem? First of all, we should multiply this side by the c, and we can obtain dq over dt c epsilon over rc minus q over rc. Now you can operate this as c epsilon minus q over rc, but we can write also as minus form, minus q minus c epsilon over rc. Now we have dq over dt equals minus q minus c epsilon over rc. If we get q minus ce to the other side and dt to the other side, we will obtain another version of this formula, dq over q minus c epsilon equals minus 1 over rc dt. If we take the integration of both sides, integral of the both sides, initially there is no charge on the capacitor, so we will start from the 0 and the q, the charge on the capacitor any moment, and the formula dq over q minus c epsilon, and the other side minus 1 over rc. I take rc out of the integration because we don't change the resistor and the capacitor, so the rc is constant. So I take it out of the integration, and you can assume here we have 1 dt, and the time change between 0 and any moment at the process. So when you get the integration of this side, you will find minus t over RC. And what about this side? If you solve this integration, you will find natural log q minus c epsilon over minus c epsilon. But I want to get an equation for q, so I need to eliminate natural log. How can I do that? This operation, if I get this as e power, it will be e power ln, so I can write directly this equation, q minus c epsilon over c epsilon, and here as e power minus t over RC. Let's arrange this formula to obtain an equation for q. You can take minus c epsilon to the other side. Q minus c epsilon will be equal minus c epsilon times e to the t over RC, and get c epsilon to the other side. You will obtain q equals c e minus c epsilon minus t over RC. We have one more last step. You can get the parentheses of c epsilon, and you will find the equation for the q as q equals c epsilon. We get parentheses of c epsilon, so 1 minus e power e to the minus t over RC. This is the equation while we are charging the capacitor, and any time of this process we can calculate the q by using this equation. And c epsilon already q, the q maximum, so any time of this charging process, the charge on the capacitor will be maximum charge times 1 minus e power minus t over RC. And if we get this equation for the current will be epsilon over R times e power minus t over RC. And as you can, e over R, remember the Ohm's law, is already I the maximum. And while we are calculating this equation, you should notice that this part should be dimensionless. So we have t here and RC here, but I should divide t by t. So RC actually is the time constant for the charging capacitor or discharging capacitor. We call this as tau. Tau is the time constant. Is constant because we are using R and C, which in the circuit they are already constant. So by multiplying them, we obtain a constant tau, which we can use to calculation of the current and the charge in the capacitor. Okay, this is our equation, charge as a function of time for a capacitor being charged. If we draw a graph about this formula, we have a spatial unit of time as tau, and if you think about after tau time, what is the current, what is the charge in the capacitor, or after 2 tau time, after 3 tau time, what is the charge in the capacitor? How we can calculate it and how we can draw a graph about it. After t time, if the t equals tau, I can write for the T as RC. So RC over RC will be 1, and this equation becomes, also this is charge, 1 minus e to the 1 minus 1. And if you calculate it, you can calculate it with your calculators easily. If you calculate it, you will find this number 0.632 coulomb. But also you can write it as a percentage of the charge inside the capacitor, percentage of the maximum charge. So if you write as a percentage, if you can multiply by the 100, and this means actually 63% of the maximum. After total time, we can say the capacitor will be charged 63% of the maximum. After another total time means now I have 2 tau, so 2 RC. If you substitute 2 RC here, now I have 1 minus e power minus 2. When you calculate it, you will find number here, but I want to write as a percentage so we can understand it better. For this calculation, we will find the percentage as 86.5. After 2 tau time, the capacitor will be charged of the maximum as 86.5%. We can move on for 3 tau time and 4 tau time, 5 tau time. I will write it basically, let's write it for 1 tau time, 2, 3, 4, 5. Okay. After 3 tau time, it will be 95% of the maximum. After 4 tau time, it will be 98%. And after 5 tau time, it will be 99.3% of the maximum. After 5 tau time, we really reach the maximum, the 100%. But as you can see here, the charge increasing, but increasing exponentially. So we obtain an exponential graph here. Why is that? Why the charge increasing exponentially? While the charge increasing, also the potential between the place of the capacitor increasing. If you think the capacitor has a potential difference on the opposite direction with the potential difference of the battery, of the power supply. So while our capacitor is charging, actually the opposite potential difference increasing. So if we calculate the I, the current in the circuit, the current will be decreased. So each step, actually the current decreased, so amount of the charge which arrives to place decreasing. So by the time the current decreasing, so the amount of charge which arrives to place is decreasing. Okay, by using these values we can draw this graph, and this graph, as you can see, exponential graph for the charge versus time to the maximum charge, amount of charge. Okay, we said that tau is constant for the time, and let's have dimensional analysis for this. Tau equals R times C is real quantity, is real unit, is a time for the tau. As you know from the Ohm's law, R dV over I, and capacitance Q over V. We can simplify dV here, and we will obtain Q over I, and I, as you know, q over dt, so you can simplify also q here, 1 over dt, you have dt, which is time, and the unit of time, SI unit of time, is second. So we prove here the tau really a unit of time. Okay, we also know the energy stored in the charge capacitor is 1 over 2 q epsilon and 1 over 2 c epsilon square, but we will talk about it later deeply. Let's talk about discharging a capacitor in RC circuit. Let's open the circuit first. Open the switch. If the switch touch nowhere, not A or not B, it's an open switch. We charge the capacitor and there's a maximum charge on it, which is Q equals E epsilon V, or if you write the potential for the capacitor, it will be Q over C. Now, our capacitor behaves like a power supply. So we charge it, it stores energy inside. So we can use this to supply energy to the circuit. So we eliminate the power supply from the circuit when we connect this switch with the point B. If we throw the switch to point B, now we have a circuit here without EMF, and capacitor behaves in power supply in this circuit. Okay, now if we write the equation again from the previous equation, just we will get the epsilon and minus Q over C minus IR will stay, but you can write also, due to direction of this current, QC equals IR, or QC plus IR equals 0 due to Kirchhoff rule. In this loop, the total potential difference is 0. So the potential difference on the resistors IR and the potential difference on the capacitor Q over C plus IR will be 0. So you can take IR to the other side here, and I, as you know, dq over dt, you can write this equation as minus r dq over dt equals q over c. Here again, you can take r to the other side to get the equation for the discharging capacitor, for the charge while we are discharging capacitor. So we obtain this differential equation, dq over q equals minus 1 over rc dt. We will get the integration of both sides. This is maximum charge, because now we start from the maximum charge of the capacitor to any moment in this process. So we have an integration from capital Q to Q, dq over q equals 1 over rc, constant again, so I get out of the integration, and here again I have 1 dt. That side, as you know, minus t over rc. The other side will be ln q over capital Q. How we can solve this equation again? We can get e power, so this side will be q over capital Q, and this side will be e to the minus t over rc, and you can get this maximum charge to the other side, and you can find the final formula for discharging capacitor. Q equals to Q, the capital, the maximum, times e power minus t over rc. So the charge decreases also exponentially. So let's draw the figure, draw the graph also for discharging capacitor. Tau time, again rc, the charge decrease 0.360 of Q maximum. And in other words, we can say in one time constant, 1 tau, the capacitor loses 63.2% of initial charge. Like previous calculation, let's try to calculate it. We can write after 1 tau, 2, 3, 4 and 5 tau, how many percent left of charge or current, you can say. They are both decreasing. After 1 tau, 36.6% of the charge will be left. After 2 tau, 13.5% of the maximum. After 3 tau, it will be 5%. After 4 tau, it will be 98 point. Sorry. It's decreasing, right? After 4 tau, 1.8%. And I want to write bigger. I don't have enough space here, so I will write here. After 5 tau time, we will have 0.7% of the maximum. So it's really close to zero. We can assume after 5 tau time, the amount of charge almost minimum, almost zero. So the time of discharging is 5 tau. We will assume it, and we will have experiment about this subject in the laboratory, and we will assume 5 tau is charging and discharging time of the capacitor. If we draw the graph with these values, you will have another exponential graph here. And the current can be found from the previous formula we found. I equals dq over dt equals q over rc, also this is I, times e to the minus t over rc. So the current also will be maximum on the opposite direction, but the maximum, so it will decrease again on the opposite side. Okay, finally we have an example. Let's solve together. Let's read it first. An uncharged capacitor and resistor are connected in series to a battery as shown in figure. If the epsilon EMF 12 volts and the capacitance is 5 microfarad and the R is 0.8 time, it's not here, we can say 0.8 mega ohm. Find the time constant of the circuit, the maximum charge on the capacitor, the maximum current in the circuit, and the charge and current as function of time. Okay, for the first one, how we can calculate the time constant tau? If you remember, tau equals R times C. R, the resistance of the resistor, and C, the capacitance of the capacitor. So we can calculate tau by multiplying R and C. If you calculate it, this is mega ohm, which means 10 power 6, and this is microfarad, which means 10 power minus 6. So when you calculate it, already they are gone. So 0.8 times 5, it will be 4 seconds. The tau is 4 seconds, or RC equals 4 seconds. What about the charge, maximum charge? Maximum charge should be C times epsilon, and the epsilon, the EMF source is given here as 12 volts, and you can write the value of the capacitance as 5 times 10 power minus 6 farad, and when you multiply them, you will find 60 microcoulombs, the maximum charge the capacitor can have. And the initial current Initially, as you remember, there is no potential difference in the capacitor, so we can write the current directly epsilon over R. The epsilon is the EMF source, is 12 volts, over R is the 0.8 times 10 power 6, and when you calculate it, you will find 15 microamperes. Okay, we have maximum current, maximum charge, and RC. Can we write both equation for the current and the charge while we are charging capacitor? While we are charging capacitor, remember the formula which we obtained. Q equals Q maximum times 1 minus e to the minus t over RC. We found RC as 4 seconds and we found the maximum charge as 60. So you can substitute them and you can find the formula of Q by the time dependent formula of the charge. And for the current, we said that the maximum current times e power minus t over RC, RC again 4 here, and we can write the maximum value of the current, and when we multiply them we will find the equation for the current. Also, when we give some values for the graph, you can draw the graph for the charge is approach while the time goes infinite. It's approach the maximum charge, and here the current always decreasing while we are charging, while we are discharging. The current will be decreased while the time goes to infinite. Okay, we can solve different type of problem about these equations, but for this class I think it's enough. You should repeat the class and you should understand them deeply, and then we will solve many problems, many examples. Thanks for listening. See you next week.